So when we are talking about is there something here? Okay, so let's start. When we were discussing about lecture 3, so let's start with a brief recap of our previous lecture. So when we were talking about, we were talking about arithmetic, and in the topic of mathematics, we continued with adders. So there were some few adders left. So we discussed about them as well: carry select adders, conditional sum adders, and carry save adders. So I gave you a task as well to do it for k by 8, assuming that the ripple carry adders, so the are k by 8. The k is the size of the numbers to be added, and you are dividing by 8. So each adder is a smaller adder. So you were supposed to do it with that as well. Um, so maybe you have tried. If not, then you still have another week for that. Okay, then we discussed about multipliers. So multipliers was our last topic. Okay, no, so sorry. Carry select adder, and then we came to conditional sum adder. It's an extreme case of carry select adder where we go for one bit. So every bit is added with 0 and 1. So there are many full adders here, but that full adder design is a little simplified design as we saw. And then the last adder that we saw was carry save adder, which is actually not an adder. It's basically a reduction circuit which reduces the number of operands to 2, and then it does that in different steps. And the way for that is that the ripple chain is broken and it's passed on to the next level. We will be using these carry save concepts in multiplier in today's lecture. So before that, we discussed about multipliers. Um Multipliers in the last class, with we started with right and left shift algorithm, and we said the right shift algorithm is a little better than left shift algorithm because it requires a smaller adder, right? So that's the advantage. So that's why we are always going to prefer right shift algorithm. Then we looked at sign multiplication as well. So we looked at initially unsigned multiplication, then signed multiplication for 2's complement number using a positive multiplier and negative multiplier. So positive multiplier is the same as an unsigned numbers multiplication, except that you have to look for the right shift. The shifts have to be arithmetic. That's the only change. When you're talking about negative multipliers, the last step has to be changed because the last bit has a negative weight, and that means that the last step instead of addition should be subtraction. Okay, so at the end we also looked at Booth's algorithm. The Booth's algorithm takes advantage from the fact that they are going to, if there are multiple ones, if they are consecutive ones or zeros. Zeros, obviously, if they are consecutive zeros, it was never an operation previously as well. But if they are consecutive ones, in a normal case, this would make many number of operations. But when you're talking about Boost algorithm, it converts it into another code in which there is just one operation or two operations being done, and an addition and a subtraction, and this saves the number of operations. So we looked at Boost algorithm, but the Boost algorithm for radix 2 is not so feasible. So today we are going to talk about higher radices, higher bases. So when you talk about radix, it's basically a base. So base 2 is not very feasible for Boost algorithm. So we are going to talk about how to improve that, how to make that a little faster. So today, okay, so we are going to start now with high speed multiplication, how to improve the time of multiplication. So if you view the multiplication as a multi-operand addition of problem, so there can be two ways to speed it up, right? One way is to reduce the number of operands. So you can do that by handling more than one multiplier bit at a time. So that's the same case over here. If I'm talking about say uh, a number like in binary, if I'm talking about 1010, that's 10. If I'm talking about, let's say, unsigned numbers, so that's 10 here. And if I multiply it with 1110, so that's 15 here or 14 here, right? Okay, so this is a binary system and this is the decimal system, right? So which one is easier? When you're talking about binary system, you have to do four operations because there are 4 bits here, right? So there are 4 bits here and you have to multiply each bit with the whole multiplicand, right? Walaikum assalam. So when you're talking about a decimal system, because in a decimal system there are going to be digits, and each digit and there are going to be many digits, so there are different possibilities, because here we just have two possibilities, zeros and ones, but here we have got 10 possibilities. So in decimal number system, obviously this is just going to take 2 steps to do, because once you're going to do it with 4, once you're going to do it with 1, right? So this means that if you have radix 2, so base 2, say for example, and base 10, so if you have got base 10 here, then this means that base 10 is obviously going to be completing the multiplication operation faster than base 2. Okay, that's something that we know as well. But computers obviously are not very familiar with base 10, so we need to have something which is familiar, which they are familiar with, that is bits. So we go for powers of 2. So for example, we are talking about taking 2 bits at a time, right? That would be base 4, right? So if you're talking about taking 2 bits at a time, that would be base 4. So base 4 would be faster than base 2. Now if you take 3 bits at a time, that would be base 8, right? So that would be much faster than base 2 and 4. So if we take 4 bits at a time, that would be a hexadecimal number, and it would be even faster. But the problem with every basis that you are increasing is that they are going to many multiples, and that's the main thing. That's the main problem that's perhaps going to come over here. So one option to speed up the multiplication process is to reduce the number of operands to be added, right? So number of steps or number of operands to be added. So this is as if you are going to handle more than one multiplier bit at a time, go for higher bases. The other thing that you can do is add the operands faster. Okay, so if you want to speed up the multiplication process, what you can do is go for any one of these schemes, and this is going to make the multiplication a little faster. So either you can have more than one bits taken at a time, that is, you are assuming that we are going for base 4 or base 8 or base 16. To remain in power of 2 means that you are still going to consider the binary number system and its powers. Obviously, decimal number system is a little difficult for computers, because if you're going to encode in that way, then you are not utilizing all the storage spaces, and then many things get unutilized, and then that's not very feasible. So we remain with base 2, 4, or 8, and all those bases with the power of 2. The other thing is add the operands faster, right? So go for some scheme whenever you're going to get different operands, you add them very quickly, like an adder, which is going to have its operand additions in parallel, right? So it's not waiting for the operands coming one at a time, but it's going to decide on that, and then it's going to add them quickly. So there can be different schemes, and we're going to talk about that later. Okay, so let's go for the first scheme. Now, in a dot notation, if you're talking about taking 2 bits at a time, then this means 2 bits are going to multiply it by 4 bits. So we talked about that earlier as well. So that if your multiplicand is of 4 bits and your multiplier is of 2 bits, then the result is going to come in 6 bits, right? So this is going to be our first operand, because 2 bits are going to multiply with, so x 2 bits are going to multiply with a, and then we can have a 6-bit number, and then the next 2 bits are going to multiply by 8, and again we are going to have a 6-bit number. Finally, we are going to have an 8-bit number. So we have shifted it twice because we are going to for base 4, and then we are taking 2 bits. So this means the shifting process also has to be doubled or tripled if you're talking about base 8. So in this way, you are still going to get the product, but see the number of operations have reduced from 4 to 2, right? So you just need 2 operations, and this means that you have speeded up your multiplication process. Okay, so each dot here that when you're talking about dots here, it represents a 0 1. When you're talking about a number which is represented in this dotted square rectangle, then you can see that they are going to be 2 bits. And then if they are 2 bits over here, then this means that there can be 4 possibilities of that. So it's going to be either 0 1 2 or 3. Now if you're going to multiply 0 with a, the answer would be 0. So that's simple, right? If you're going to multiply 1 with a, that's going to be a. So that's also simple. Now if you're going to multiply 1 0, so let's say if there is a 1 and a 0 over here, so this means you are talking about 2. And if you're going to multiply 2 with a, the answer would be 2a. So 2a again is easy to compute, because 2a means you have just shifted a to the left. So if you're going to shift a to the left, that is as if you have computed 2a, right? So 2a is also simple. Now if these 2 bits are 1 and 1, now if these 2 bits are 1 and 1, that's the difficult part, because that means you are going to multiply it with 3. And 3a is not an easy multiple. Now to compute 3a, you cannot do it directly. So when you're talking about base 4, it's easy. It's faster than base 2, but the problem is that you have got many more multiples than base 2. So here you have got 1a, 0 and 1a that was previously in the base 2 as well, but the new multiples are 2a and 3a. If you go for base 8, then you are going to have 5a, 4a, 5a, 6a and 7a's as well. And then the things get a little more difficult, right? So the problem is with these multiples. If you have these multiples with you, then obviously the multiplication is going to be simple. But to compute 3a, so a can be anything. A can be any combination of 4 bits. So you can have anything as a. To have 3a means that this is itself a multiplication operation. So you're trying to do multiplication, but then you need a multiplication before that as well, right? So this is a little problem over here that we are going to address. This is what we have discussed, that the number of cycles are halved, but there is a difficult multiple which is 3a, and it should be computed first before you start your multiplication process, right? So you should have your 3a computed, because no hardware unit can compute 3a simply like 1a or 2a or 0. So that's easier operation, but 3 is a little difficult operation. So you perhaps need to have a special operation for that. So this is one way to do that. So we can have another register, and we have a multiplexer, and then this multiplexer input goes to the adders, and the multiplier bits are going to select the select lines, are connected to the select lines of this multiplexer. So if the multipliers bits are 0 0, then obviously 0 goes to the adder. If these bits are 0 1, then a goes to the adder. If these bits are 1 0, then 2a goes to the adder. Remember in the previous class we discussed about a circuit on multiplier. That was a simple circuit which has just got 2 inputs, 0 and a. So either 0 goes to the adder or a goes to the adder. This is what we did also in the examples that we did for right shift algorithm, that we were either adding 0 or either adding a to it, right? But in Boost algorithm, when we practice Boost algorithm, we said that okay, we can add a to it or minus a to it. That's the complement, and that's very easy to compute as well. Because you just need a NOT gate and invert everything and add 1, and that's a 2's complement. So that's also easy. So these 3 are easier ones. So you can just you don't need a special cycle for that. You can just do it easily. We are going to look at that as well. But then we have a 3a over here. So what we are going to do is, whenever we are going to have an a over here, so we are going to add 2a plus a. So this means that we have to do one pre-computation. So a pre-operation is required for multiplication. That is, we are going to shift a and add it with a, so that this becomes 3a, right? So I'm going to say again, we need a register, and in that register, what we are going to do is, before starting our multiplication, we are going to, whatever the multiplicand we have, we are going to shift it to the left once, and then add it with its own value, so that this becomes 3a. and this is going to be stored in the register. So once we have 3a with us, then we can, if one comes over here, then we can pass that value to the adder, and it's going to add 3a. So this can be one way to resolve it. But the problem is that you are going to have half of that plus one cycle, because this one cycle is always necessary to form 3a, right? So rather than having k cycle, k by 2 plus 1 is good, right? So we have almost halved it, but still it's not exactly half. So we have added one cycle more. So can we reduce that cycle as well? So can we have another way to compute 3a without involving an additional cycle in every multiplication operation? So this can be done with another way. Now 3a can be assumed as 4a minus a. That's another way of assuming 3a. So 4a is an easier multiple. When you're talking about 4a, that means you have shifted it to the left twice. Instead of once for 2a, you are going to, if you're going to shift a twice, that would be 4a. But 3a can be computed as 4a minus a. So that could be one of the ways to do 3a, right? So that can be done as well. Okay, so we are going to look at one of the circuits where we can perform this operation here. Now this is a simple circuit here, and this circuit involves a multiplexer which has got 4 inputs. So there is no 3a input, rather there is a minus a input, and we are going to assume this 3a operation as 4a minus a, right? But you can see there is no 4a operation over here. So what we are going to do is so I'm going to just discuss this here. So what we can do is, yeah. So if I ask you to multiply 7 with 3, right? So that would be 21. Okay. So if I'm going to talk about that in binary, so that is 111. Let's go for 4 bits. Multiply by 0011, and that would be 21. Okay. Now what we are trying to do is, instead of multiplying with 3, let's have another thing, which is 111 multiply by 100. That's for 4, minus 001. That's for 1. That is also 3, right? So when you have 4 minus 1, that's also 3. Okay. So if you do it in this way, then what you can do is you can have this operation first, and then in the next step you can go with the multiplication with 4, right? So I have to multiply 7 with 4 and 7 with minus 1, right? So that is going to give me the same thing, because 7 with 4 is going to be 28, minus 4, that is, sorry, minus 7, 28 minus 7, that is still going to be 21, right? So that's the same thing. So what I'm going to do is, I'm going to first of all do this operation, 7 into minus 1, and that is going to give me just minus 7. Okay, so it's not 21, it's minus 7. And then I'm going to shift the whole thing, that my answer, because in each step we are going to shift it to the right twice. It's a right shift algorithm. So if you're going to go for base 4, we are going to shift it to the right twice, which means that the partial product is in fact shifted to the left, and it's same as what we did in a normal multiplication, where if you put 2 crosses for the next level. So we are going to the higher numbers, right? So this is as if we have multiplied by 4. So when we have multiplied by 4, our answer is multiplying everything by 4. So all the multiples that you have done, like for example you have multiplied -7, that is also multiplied by 4, and then you don't need to subtract it with 28 anymore. You just need to subtract it with its normal value, divide by 4, which is just 7, right? So I'm going to come to that. uh, yeah. So here what we are talking about is we have got 0 and a and 2a. These three were previously there as well, and then we have introduced -a, but then we have introduced another circuit, which is and a flip-flop here, right, which is going to change the bits. So if your multiplier bits are 1 0, what's going to the multiplexer would be something different depending on what's there in the carry flag. So this is going to change it according to the carry flag and the bits coming from multiplier, and a new select bit is going to go over here. And for that we need a table that is going to tell us what operations are required. Now this C flag is actually a correction flag, right? So this is basically a correction required. So whenever C is 1, this means you need correction here, right? So let's go with 0. So let's have no corrections, for example. So for example, let's go for the 4 combinations where C value is all zeros, right? So we have got 2 bits 0 0 coming from the multiplier, and the C bit is 0, the correction bit is 0, no correction is required. This means if 0 0, then 0 should be passed on. So the inputs to this multiplexer should be 0 0. That's simple, right? And no correction would be required in the next step as well. If you're talking about 0 1 with a 0, right, then also you're going to pass on 0 1 to the multiplexer and no correction is required. If it is 1 0 coming from the multiplier and previously there was no correction, then 1 0 is going to go to the multiplexer, and then still no correction would be required. The problem comes when the multiplier bit is 1 1 and there was no correction, right? So let's go with this scheme here. Now when it is 1 1 and there is no correction yet, this is the first step, which is having 1 1 over here and there is no previous correction. So what to do over here? So when it's 1 1, what you're going to do is you are going to select the multiplexer control to 1 1, but you are going to say that in the next step I have to correct it because this multiplication is incorrect. So what you're going to do is set the carry flag to 1, right? So this is the first step where you did not have a correction and you placed a carry flag as 1. So this is one case, right? Then what's going to happen when we have correction as 1s? So if you have a correction in your previous step, what to do? Now if the previous one was 0 0, now if the multiplier bits are coming as 0 0 and there was a correction from an earlier step, so what is required is now 0 0 converts to 0 1. It increases by 1. So if it is 0 0, it becomes 0 1. That is, instead of passing 0 to it, you're going to pass a to it. This is the correction that is required. So as I mentioned, 4a minus a. So you did the minus a first, but then you changed the step. So that is, everything is shifted to 4. So next step, you just have to, instead of 0, go for a. Instead of a, go for 2a. Instead of 2a, go for 3a. But then 3a again is a little complicated thing. So we are going to come to that once more. So now in the next step, if it was 0 0 and the correction was required in the previous step, it becomes 0 1. So instead of 0 passing to the adder, you're going to pass a to the adder, and everything is going to be fine because then you don't need any further correction. Now if it was 0 1, normally a should have gone, but if it was 0 1 and a correction was required, you are going to change it to 1 0. Okay, you're going to change it to 1 0 and everything is fine. Now if it was 1 0 and a correction was required, Now, if it was 1 0 and a correction was required, then it changes to 1 1. But whenever it changes to 1 1, this means that you are already subtracting it with, multiplying it by a different factor, not actually 3a but minus a. So what is required is you need a correction in the next step. So you are going to multiply it with minus a still, but you need a correction in the next step. So if it is 1 0 with the correction, then you multiply it with 1 1, and then you have the correction bit as 1, which means that still you need to correct it in the last step. If it is 1 1 and a correction was required in the last step, the same happens, that now it's going to be converted to 0 0, right? So it's shifted to 0 0, and again a correction is step. So in this case, if it was a correction required over here, you are going to do it with 0, and then you're going to resolve that in the last step here. Now, what is the difference between this one and the previous one that we did? So in the previous one, we talked about having k by 2 plus 1 steps in all multiplication. But in this case, we are going to have in majority of our multiplication just k by 2 steps. So we have saved just one step, but it's still a big achievement. So we are not doing any pre-computation. We have reduced that 3a and the register, the actual register that we are using, by using a simple flip-flop, which is going to just take care of that, and corrections are required. So if your last step also needs a correction, then you need perhaps one more cycle for that, right? So if you have say for example 8 bits in your multiplier, you're going to take two bits at a time. So this means you need 4 steps to complete the multiplication. If your last 2 bits are having a correction coming from the previous case, and they are going to set a correction for the next step, then you need one more step to correct your input, right? So but this can be one way to go for a base 4 multiplication, right? Any questions here? So this is normally a little difficult for student to understand the first lecture, but if you can go through that yourself, I'll provide you with the text as well. So this is one way to do radix 4 multiplication. So I have just discussed it with you because when you're talking about multipliers, there are different types of multipliers. Obviously, this is not the best scheme, right? This is not the best scheme to do multiplication like this. But this is one way to do it, that we provide all the multiples to the multiplexer, and then these multiples, whenever we need them, we give that to the adder and we add them, right? So if we go back to our multiplication operation, then we can see that this multiplication operation is actually addition of multiples. So if I need to add multiply 74 with 27, so what I'm doing is I have two operands here, 7 multiplied by 24 and 220 multiplied by 74, right? So then I'm just going to add them, right? So this is what I'm doing here, right? So the problem is that if I have an adder with me, which has got all the multiples of 74, like 0, 74, 74 multiplied by 2, which would be 148, 74 multiplied by 3, you can compute that as well, till all of them. So if I have till 74 multiplied by 9, so if I have all the multiples with me pre-computed, then my multiplication becomes easier, because whatever I have to, if I get 2 over here, I'm going to pass 148, right? So if I've got a 7 over here, I'm going to pass appropriately, what would that be, 500, 518, 518, I think so. Yeah, so 518 would be passed on, and 148 in the second case. So this is actually what is required. right? So if I get a 2, if I have a 7 as my bit, I'm going to pass 518. If I have a 2 in, I'm going to pass 148, and then my task is just to add. So my adder is going to pass all these multiples. The problem with this is this is easy. This is actually the same thing. Uh, in binary number system, going from 74 to 148 is very easy because you just have to shift it once. But the remaining multiples are quite complicated. So you cannot do that with a simple circuit, right? So some of them are easy in binary, like 7 multiplied by 4, 74 multiplied by 4 would be easy because you're going to shift it just twice. But the remaining are complicated. So one way to do those multiples are compute those multiples is pre-compute them and provide them to the multiplexer, and then sorry, this is a multiplexer, not the adder. So oh, this is a multiplexer, not the adder. So provide them to the multiplexer, and then everything is fine. And this goes to the adder where you're going to give any one input and then it's going to add that. Okay, so it has to add 518 with a shifted version of 148, and you got your answer. So the problem of multiplication is actually addition, but you should need to know what is required for it to be added, and this is here. Okay, so this is another way of looking at multiplication, that if we have got all the multiples, we just have to select the right multiple. So it's the multiple or a shifted version, and you can talk about shifted version, or if you're talking about right shift algorithm, we are basically talking about doing it after shifting it. So one bit uh, gets confirmed, and then we are going to go on with the other operations. So this can continue on and on and on. So if you have a number of bits here, that's going to be the same process over here. So this is how multiplication is being performed. So the problem was these multiples. So when you're talking about 3, the problem is complicated because 3a cannot be done. So one way to do that is to use minus a instead of that, and then you have to correct it in the next step. So this is one way to do multiplication. So but this is not a very efficient way if you're talking about higher lattices, because if you're talking about base 8, uh, you are going to have many multiples which are going to be problematic. Like for example, if you have 3a, you can do it like this, but 4a is simple, 5a, 6a, 7a. All of these 5a, 6a, 7a are going to be complicated, right? And then you perhaps need more corrections and more techniques to do that. So that's not an efficient way. So let's go for an efficient way, which is again a Booth algorithm, but this is now a modified Booth algorithm where we are going to talk about doing it for 3 bits at a time. So in the previous class we looked at 2 bits and converted that into a symbolic form having 3 symbols, 0, -1, and 1, right? Now we are going to talk about a modified Booth algorithm in which we are going to look at 3 bits and we are going to convert that into a single bit, or not single bit, a single symbol, but you can have 5 symbols here, right? So you're going to have 5 symbols here, and these symbols would be um, -2, okay, -2, -1, 0, 1, and 2. So these are going to be our 5 symbols. So we are going to convert that into this form. So previously what we did was in Booth's algorithm in the last class, we looked at -1, 0, and 1, right? Now when talking about radix 4, your symbols are -2, -1, 0, 1, 2. Now you can see very easily over here there is no 3. That's the main thing. That's the main thing. You are not concerned with any of the code, those complicated multiples. If you go for base 8, what you need is -4, -2, -1, 0, 1, 2, 4. All of them very easy to compute, right? So this is the advantage of modified Booth algorithm. We are going to look at modified Booth algorithm for radix 4. The same can be done for radix 8, where you're going to have these symbols, and all of them can be pre-computed. So you don't need a specialized circuit for computing any one of these multiple or these multiples, right? So that's why Boost algorithm in this case is going to be very good for us. Okay, so what we are going to look at is 3 bits at a time, and this is actually converted into the form where we are looking at 2 bits, and then we can convert it into this form, or 2 bits over here and we can convert it into this form. But let's just ignore those y's over here. Let's come to z over here. So we are interested in these z symbols, right? So these are our radix 4 digits. Okay, so so if you have a 0 or all ones, this means there is no change. So if there is no change, this means that no activity is going to perform, so that both of these converts to 0. Okay, so if they are all zeros or all ones, both of them converts to 0. So if there is a 001, then this means that the one has the end, the one string has ended, and then this means that you need to do a positive operation to make that change here. And then similarly for 010, again a positive operation. 011 also means that since the one string has ended, you are now going to do a positive operation. uh, and then if there is a 1, this means the one string may be starting. In this case as well, one string may be starting, and in this case as well. So in all these there are negative operations here. So it's easy to remember if you're going to write it like this: 001 till 111 in the sequence. You can see the sequence over here is 0112 minus 2 minus 1 minus 1 and 0, right? So let's try to do one example here. So now we have to recode it. Let's try to recode it. So this is the recorded version of y's, but we are interested in recording this operand x into z's, right? So we have 1 and a 0. Okay, so we have got a 1 and a 0, and then there is, this is our first one, so we have to add an additional 0 over here. So we can add an additional 0 over here. So we can add an additional 0 over here. Okay, so this becomes 100. Now when this becomes 100, 100 means minus 2.
Minus 2.
Yeah, minus 2. So you can have a minus 2 over here, right? Now, since we have concerned with, we have already looked at these 2 bits, so we are going to look at only the last bit that has been utilized in the previous one. So now we are going to talk about this 111. So 111 means no change, so nothing is going to happen over here. Okay. Then we are going to have 101. So likewise, we are going to do that. 101 again. 011, which was mean 2 over here, and 110, which means minus 1 over here, and 1011, which means 2 over here, and finally 100, which means minus 2. So um, this is a 16-bit number, right? So this 16-bit number is when you're talking about Booch algorithm, you're always talking about signed numbers. So it's a negative number. So this is a 16-bit number, and we normally need 16 operations, 16 steps. Sometimes when there is a 0, you don't need any operation over here. So the number of additions in a normal multiplication would involve 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 addition operations. If you're considering 0 to be added as also as an operation, so then this means you have got 16 operations. But when you're going to convert it into its Boost equivalent form, it's going to be half, because we are going to consider just 2 bits together. So 3 bits converted into a single symbol. So this means you're going to have 8 symbols at the end, right? So this is going to be our Boost recording. Okay, so yeah, so this is what we did as well. So yeah, so this is good. So let's take an example here. So let's take an example. Um, okay, so what can we do over here? Right, so this is example of two numbers that we need to multiply: 0 1 1 0 and 1 0 1 0. Okay, so you did that previously with uh, Redux 2. Let's try to do this with Redux 4. Now, if you do it with Redux 4, the first thing we have to do is recode this x into its equivalent boost recorded form, right? So for that, we need to consider 3 bits at a time and then convert that into the symbolic form. So since this is the first two bits and the LSBs and the next to it, so we add an additional 0 over here. So this becomes 1 0 0. So 1 0 0 means -2. So we put -2 over here, and then 1 0 1 means -1. So we have -1 and -2. Okay. So these are the two symbols that we have over here. Any question?
अरे रजिस्टर का कमाल है रजिस्टर
Iqbal Aziz. Iqbal Aziz,
अस्सलाम
your
वालेकुम सर
Walaikum Assalam. Your mic is on. Please mute yourself. Yeah, thank you.
सॉरी सर
Okay. So this is your first class, right? Where were
यस
you?
सर
Where were you previously?
सर आई रिजाइड इन औरंगी टाउन देयर इज द मेजर इशू विद द इलेक्ट्रिसिटी
Okay.
जिसकी वजह से ज्वाइन नहीं कर पाता अभी भी बाहर से चार्ज करके लाया हूँ तो बैठा हूँ लैपटॉप
Okay. 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 So we were talking about multiplication using modified Boost algorithm. So I'm going to continue with that, right?
ओके सर कंटिन्यू
So we were talking about yeah, where were we? Yeah, here. So we were talking about first of all converting that into its equivalent boots recorded form, right? So 1 0 0 converts to -2 and 1 0 1 converts to -1. So what we need to do in these steps now is to multiply a with -2, which is -2a, which is actually the complement of the shifted a. Okay, -1a, which is just the complement of a, right? So let me just have this thing over here. So when we're talking about these symbols here, so when you're talking about these 5 symbols here, if you have to multiply it with 0, that same thing is going to come over here as an answer. So 0 means if you're going to multiply anything with 0, it becomes 0. So that's easy, right? So we are going to multiply a with these. So a with 0 means it's going to be 0. That's easy. A with -1 is going to be -a. Now what actually is -a? It's just a 2's complement. So it's a 2's complement here. Now how to compute this 2's complement? When you have got a in 15 bits or 16 bits or any number of bits, what you can do is use an inverter and add a 1, uh, add the 1 at the LSB. Now this addition of 1 can be done along with that, because if you have got an adder over here, right, so it's going to get a C in, right? So it's going to get a C in because it's an adder. So if you want to do the complement of a, so what you can do is pass on a to, say, okay, so one thing, um, I need a multiplexer also. I'm going to redraw this. Okay, so I need a multiplexer as well. So one of the input is my partial product of the last step, the other should be a, or the new value, and for that I need a multiplexer over here, and this mux is going to have two inputs. One is going to be a, and the other is actually the complement of A, right? By complement of A means that there is an inverter over here which is going to complement the whole thing as A. So you have got A over here, and so for example, if A is going to be 1011, so what from this side, from the zeroth side, what you're going to get is 1011. From the one side of this multiplexer, you are going to get the complement of this 10100. Okay, so you are allowed to pass any of these two values, A or the complement of A, right? So this is a small circle shown over here. Actually, I should have okay, I should have made that a little bigger, but okay, so I'm going to write that as a little bigger one. So let me just have this as a multiplexer. So this is my multiplexer, not adder. Okay, so I'm going to have an adder separately. Okay, so this is my multiplexer, and the multiplexer input goes to the adder, which has a carry input as one of its input, right? So if I need to have the two's complement of any number, what I can do is so let me just write a number first. So let's have a number 10. So 1010, right? So these are in 4 bits representation of 10. So what you can do is to represent either positive 10 or minus 10, you need to have an extra bit. So let's talk about plus 10. Now I need to convert that into its equivalent form of minus 10. So we know what the 2's complement of this should be. It's actually going to be minus 16 plus 6. So we did that in the last class as well. So minus 16 plus 6 would be something like this. So that this is 10 and this is minus 10, right? Now we need to have a circuit which can both pass 10 and minus 10 to the adder. Okay, so what we do over here is we can have a value passed on its zeroth input and have a little complement over here. So we can have so this is actually a small circle which is representing an inverter, right? And this is the one input of the multiplexer. Okay, so by inverter we mean simply that every bit has to be inverted. So 1 gets to 0, 0 gets to 1, 1 gets to 0, 0 gets to 1. So if you're going to go for the same example 0 1 0 1 0, so the zeroth input is going to give this number, but the one input is going to give just 1 0 1 0 1. But this is not what we wanted, right? So this is not what we wanted, and there is a difference of just 1 between this number and the number we wanted. Okay, so what can we do for that? What we can do is have a Cn of 1 over here. So if the carry in is 1 to the adder, this is going to convert this thing into 10110, right? So actually we had to add the adder with the partial product coming from the last stage and this value. So what we do is add this value and the last value and 1 together. This one is actually, if you're going to add this one to this thing, this becomes this. So this is as if you have adding minus 10 with this last partial products result, right? So this is how you can use a and minus a without any complicated circuit. So you just need a multiplexer and an inverter, right? And the same input which is going to the carry input also is the select line for this multiplexer. So if the carry input is 0, this is going to pass on normal A. If the carry input is 1, then it's going to pass on inverted A and also give 1 to this adder, which is going to convert that into its equivalent 2's complement form, right? So this is the same thing that's required over here. So when you're talking about minus 2, actually what we need is a should be shifted, or you can do it in any way you want. You can shift first and then do the complement, or you can complement first and then do the shifting. So both of them are possible, right? So minus 2 means that you have to do it to do a shifting of a twice and also complement it, okay? Which would mean that 0 1 1 0 converts to um, what will that convert to? So if I'm going to write minus 2 or a over here, that would be um, so 0 1 1 0. That's the normal thing, and I add the extra 0 over here to make it positive because this is a positive number over here. So 0 1 1 1 0, I've added the 0 to avoid confusion, right? So I need to first of all negate this. So this becomes 1 1 0 0 1 and add 1 to it, right? So that becomes 1 1 0 1 0, right? So this is minus a. This is the value of minus a. So if this is a, then this is your 2's complement minus a. And we need minus 2 of a, so you just have to shift it to the left once more. So this becomes 1 1 0 1 0 0. This becomes then minus 2 of a, right? This becomes then minus 2 of a because this is a. And so when you're going to practice a lot, then you don't need to do this thing like this, right? So when you're going to have a little practice, what you can do is, instead of doing this addition and converting that, what you'd simply do is you check on from your LSB side till the first one that you get, and then you just copy the same thing in your answer till that one, and then you're going to invert that, the remaining portion. So 0 and 1, so that's the first one that we obtained, and then the rest of the portion would be the complement. So 1 gets 0, 0 gets 1, and 0 gets 1. So that is going to be your answer. So you don't need to do it in these two steps. You can directly do it in this way, checking when is your first one coming from the right hand side. So your first one goes in your answer as it is, but the remaining bits are then going to be inverted in your answer. Okay, so and minus 2a is the shifted form of a. So what we need is minus 2a and minus a. So we have pre-computed both of them, or not pre-computed, actually there is a circuit for that, and that can do it on the fly. So you don't have to do any special any special operation for that. So if you are going to write that in 6 bits, it would be something like that. If I write minus a in 6 bit, I just have to add an additional 1 over here. That's a sign extension, right? And this also converts to 6 bits. So this is 1 1 1 0 1 0 and 1 1 0 1 0 0. So let's start the operation. So let's start the boost algorithm process. So again, the same thing. We started with having the partial product register as all zeros. Okay, so we are going to start with all zeros. Why we have used 6 bits is because the maximum that we can get is because we are talking about 2 bits and 4 bits. So the number we can get is maximum 6 bits, right? So the first thing is minus 2. So we have a computed minus 2 1 1 0 1 0 0. So we are going to add 1 1 0 1 0 0 with this, and this is going to be our result. Then we are going to shift left twice, right? Sorry, shift right twice. So shift right twice. Now 0 goes over here, 0 goes over here, 1 goes over here, 0 goes over here, 1 goes over here, and then 1 goes over here. What about these two positions? What about these two positions? Because the last one went over here. So because this is a thematic shift, right? Because this is a thematic shift, so this means the sign is should be preserved, which means that whatever sign value is over here has to be on these two positions. Okay. Now remember that in Boost algorithm we are always talking about sign numbers. Okay, so if you are still having problems, then what you can do is have an extra sign bit in your process. So when you, in your steps, so that everything is clear to you. So what goes into the two bits that have been shifted out. So these two bits have been shifted out in the space for two bits. So these two bits should be the same bit, which is 1 1 over here. Okay, so then we have to do it with minus 1. Okay, so minus 1, we have computed minus 1 as 1 1 1 0 1 0. So we are going to add 1 1 1 0 1 0 with this. So it's going to be 1 1. If there are any carries, you can just ignore them. So 1 carries at the ends. So 1 1 1 1 plus 1 0 1, and 1 plus 1 plus 1 1 1, and 1 plus 1 1, and then there is a carry, so you can ignore that carry. So this is your last step here, and then you need a final shift to make it complete in 8 bits. So let's check whether we have obtained the right answer, because we have just used 2 steps to get this answer. So our number was 6 here, plus 6, that we need to multiply it with. What is this number? 1010?
So 10.
No.
Oh, uh, minus 8, minus 4.
Hmm? Minus 8.
Sir, it's a minus.
Huh? Kya? What? Who said that?
Sir, a minus 6.
Minus
minus
6.
6.
Right. Minus 6 is the right answer, because we are talking about minus 8 plus 2, that would be minus 6. So we need to multiply 6 with minus 6, so the answer should be minus 36. Right. So let's see whether we have the right answer with us. So this is the last one over here. So this could be taken as a negative weight. So we have a 0, 1, 2, 3, 4, 5, and 6. 2 raised power 6 means 64. So minus 64. Right. So minus 64. And then we have a 16 over here, and a 12 over here. So 16 plus 12 is a 16 over here, and this combined is actually 12 over here. So 16 plus 12 is 28. So minus 64 plus 28 is going to be what? 36. Minus 36. Right. So so we have obtained the right answer. That we have checked as well. So we have obtained the right answer here. But you can see that we have obtained this answer only in 2 steps. So instead of just doing it 4 times, we just did it 2 times. So we have just two additions and 2 shifts. 2 additions and 2 shifts, and our answer is there. Okay, our answer is there with after 2 additions and 2 shifts. Right. So this was about the process of Boost algorithm, but obviously in this course we are not really interested in only the algorithm, but we are also interested in uh, how to uh, how to do that at the hardware level, right? So in the next slide, I'm going to show you the hardware implementation of the Boost algorithm, which is having so let's start from the top. So we have got a multiplier and a multiplicand, and then we have got another uh, kind of a flip-flop here, which can store a single bit, initially 0, and this is going to basically look for the bits which are shifting out. So we are going to always talk about 3 bits. So we are going to look at 3 bits. So when you're talking about hardware, obviously you cannot have minus 2 and minus 1s over there, right? So you need to think about a different logic. So what you do is you look at 3 bits and try to do your operations on the fly, right? At runtime. You are going to get 3 bits, and you're going to prepare a logic circuit for that, and then it's going to give you different signals. So signals that we need are negate, 2, and non-zero, right? So non-zero is actually going to be 1 for all values except 0. Okay, so 0 for 0, it's going to be 0 because that's only the non-zero value over here, and then for all the other ones it's going to be 1. Okay, so this is a simple circuit. This multiplicand, that was the value a, is going as it is A in the multiplexer, and then on the zeroth input, and the sign of A, which would be the most significant bit of this multiplicand, because this multiplicand is not shifted from the multiplier shifted. So you can take that sign bit of A and append it with this input. So if it is a k bit uh, value, what's going to the multiplexer is actually k plus 1. Okay, so k is coming as it is from A, and you have appended the sign of A as the extension to that. So if it's k, then this multiplexer is going to have one more bit, which is going to be the sign of. So this is as if you have extended it to k plus 1 bits, right? So this is easy here. Okay, and when we're talking about this this 2 multiplied by 2 value over here, so that's also simple. We are not shifting it in over here. We're just passing a over here and appending it with 0. So a 0 at the end means you have shifted to the left, and as if you have multiplied by 2, right? So there is no shifting happening over here. Just A is going into the one input, the first input of the multiplexer, and you are appending at the very end the LSB side an additional 0. So this is going to be a k plus 1 bit number, and that would be 2A. So this multiplexer is getting 2A and A, and both of them are k plus 1 bits, right? So both of them are k plus 1 bits, and then there is a select input which can select either this or this, and this selected input is uh, controlled by this two logic over here, whether you need to select this number or this number. And then there is an additional negate logic which is going to go to that adder, as we have mentioned that if you need a negation, you have to have a 1 over here which will do the subtraction operation. If you need a 1 over if you need an addition, that's going to give a 0 over here. And this is how you have obtained 0 for all these positive values and 1 for these negative values. So this is your first input, right? So you need a decoding logic for that, and then this can be done using these 3 bits. You can make a truth table for that, and then you can design how to have a 0 or a 1 at this input, looking at all the possible combinations at the input, right? So you did all this in your digital design logic course. I'm not going to do that here. Okay, and then 2 similarly is going to be only 1 for whenever we need a 2. So it can be -2 or 2, but these are the only 2 positions where we are going to use this input, right? And then for the next one, non-zero, that's only going to be 1. That's only going to be 0 for a 0 value over here, and for others it's going to be 1. This non-zero is actually working as an enable input to this multiplexer. So if it is not enabled, then the input is going to be 0, right? So this is a little trick over here. Normally a multiplexer is going to give either its input on the zeroth, either the zeroth input or the first input. But here it's shown as an enable signal over here. So if it's not enabled, if the whole multiplexer is not enabled, it can give a third input as well, which would be 0. So like this way, we can have 3 inputs coming out from the multiplexer: a 0, a or a 2A. And additionally, we can have a negate signal, which is going in the same way that I draw in my diagram over here, that we can have an additional like this here. So that this is how you're going to have either an addition operation happening over here, or a subtraction operation happening over here. Okay, so this is the same thing that we discussed over here. Okay, so that's going to go and control those adders input. So this is about doing multiplication in a fast way. So I'm going to have some questions from your side. We have some time over here till I go to the next topic, which is to go for full CSA tree. So I'm going to have some questions from your side. Yes, anyone? Is this okay?
So
Yes, sir.
in the recording logic, the
I couldn't get your answer question. You're talking about recording logic. Miss Shirina, can you repeat your question again? You're talking about recording logic. You want to talk about anything here?
Yes, sir. The three signals, non-zero, two, and negative. Please, can you explain them again?
Okay, so when we're talking about recording logic here, so that's a simple circuit that you can make yourself. You can design it yourself. For that, you need some basic knowledge about digital logic design, and every one of you have that knowledge. So what we do over here is we have some inputs coming into that, and these are three inputs which are the multiplier bits, and this is how we discussed about how to convert a 000 into a 0, and 111 into a 0, and 001 into a 1, and similarly for other inputs. So the main thing here is if you're going to get a 110 over here, you need to have any one of these at the output. So for that, we need to go to our previous slide where we are talking about this diagram here. So if you're going to get a 110, you're going to get a -1, right? So you need to have a -1 over here, but this -1 is further divided into three inputs, right? Because this -1 cannot be stored in binary form. So you are going to store that in some control signal form, where you're going to generate some different control signals for these symbols. So -1 means you are going to have a 1 over here, a 0 over here, and 1 over here, right? So this is what we have decoded here. So a negate input should be 1, because you are talking about negating it in the adder. You want to negate it, you want to subtract it. So you want to have a subtract operation for this input, and you don't need to shift it, right? And this is a non-zero value, right? Which means that the multiplexer is going to provide something, right? So all these control signals are actually basically enabling this multiplexer to generate either 0A or 2A, these two control signals. And this the control signals is basically controlling the operation for the adder, whether you need to add or you need to subtract. You're going to subtract only when you have a negative value, which means only for these two values this symbol should be this control signal should be 1, otherwise it should be 0, right? So you can have multiple ways to design this recoding logic, right? So you can just go through and design a K map for that. A very simple thing to do. You have these three bits. You know when to get a 1 and when to get a 0. Which inputs are going to generate a 1 and 0. So go back to that table. This is your complete table. You need to know when am I going to get a negative input. So you need a negative input in these three cases only, right? So these three are going to give a -1. So what you do is you design through a K map, or you can do it simply without a K map as well. And then you're going to get a 1 over here whenever these three input comes, otherwise it's going to be 0, right? So you can have those AND or gate logics over here. So it's a very simple circuit, right? And then similarly for twos and non-zero. Okay.
Okay, sir. Thank you.
Any other question?
Current condition of minus digit, then it's going towards the add subtract control. Can you please review it a little bit again?
I cannot hear your question clearly again. I don't know why maybe I'm not getting that clear signals. Can you write it down in the chat?
Sure, sir. I'll write it down.
Yeah, please. Okay, so the question is the negate goes to add, subtract, control. How will it compute 2's complement and add it to main circuit? So this is what I defined over here, that when we are talking about an adder here, the adder is going to get one input, right? So I'll just draw this once more. So now we have an adder which is not shown in this diagram. uh, this input is coming from your multiplexer, right? So this was the multiplexer, and then there was a control signal coming in, which is actually the negate signal, right? This can be treated as C in or carry in for this adder, right? So carry in, if it is going to be 0, this adder is going to add. If it's going to be 1, this adder is going to subtract, right? Okay, so once one thing more over here that's required is that this negate input is actually not only going into that adder, it's also going to control this complementary input over here. So A to A, or A 0 A or 2A. So what you need here is something similar to what we draw earlier, that we can have another multiplexer here which is going to get these values coming from that point, right? And their inverted forms. And this negate signal is going to select that to the adder as well. So this the same signal is, so if you're getting a 0 A or 2A over here, and you need a minus 2A, then there should be a 1 over here. So this means you should connect it to the one input. Should connect it to the one input. So this should be 1, this should be 0, right? So if you need minus 2A, so the circuit that we have seen here has computed 2A. Okay, so it has computed 2A. It's going to come over here, and it has also computed negate signal. So that negate signal is going to go over here. That 2A is going to both the normal and the complementary side. So you're going to have the ones complement of 2A passed on to the adder with a 1 to the carry in, which is going to compute minus 2A. This is how it's done, right? So this circuit here that we have seen here is missing some part from the bottom, right? So it's written here to adder input and to control subtract logic. So but the main thing that it's showing here is how to convert these values into a logic to for multiplication. Okay, so this is how it can be done. And where is going to be input in this main circuit? What is going to be input? uh, the adder is going to come over here, right? The adder is going to come over here. The multiplexer that we have just drawn is also going to come over here. So you need an additional multiplexer like that and adder over here, right? And that's required over here. And then what you need is the same thing that we did earlier. So what we did earlier was we had inputs which are stored in a partial product. So I'm going to, if I draw this whole thing together, then this thing, the circuit that we have seen is going to come on top of this, right? And this is the adder. So adder has got one input coming from this. What is the second input? Second input is the partial product, your P, right? That's shifted in each cycle. Uh, this thing here, this thing here, right? So this is your um, second input. You need to, oh, you need to add this P over here. Oh, just keep on selecting this laser pointer. So this thing here, this is your second input, right? So you have to add P with this number over here. Purpose of what? Initialize 0. Um, is that okay? So this input here, yeah, this thing is for the recording logic. As you have mentioned, we have to look at 3 bits at a time, right? So when you're going to record your multiplier, for example, your multiplier bit is 1010, right? And you need to compute the 3 bits. So you don't have the third bit over here right now. So initially it has to be initialized to be 0, and then you get 100, right? So this and when you're going to do it for the next step, you are going to already shift it to twice over here. So when you're going to shift this twice, this bit over here. So if I'm going to talk about this first, so initially it's going to be 0, but then if you're going to shift it twice, then this thing goes into that initial bit, and so that whenever it's going to take 3 bits, only the last bit is shifted into that particular flip flop. So this is initialized to initial. This is basically initialized to 0. It's init 0. It's initialized to 0. So this is a flip flop which is initially initialized to 0. So you're going to look at 3 bits, but after one operation, these 2 bits are one of that. The last bit, which is x plus 1, becomes x minus 1 for the next step, right? And this is how you can do it. Okay, any other question here? Okay, so if there are no further questions, then let's take a break. Let's take a short break of 15 minutes. I'm going to come back at 7:45, right? So we are going to have a break of 15 minutes, and then we are going to join and go on with our. We are going to continue with the remaining topics, right? Okay, so I'm going to pause my video here. I'm going to stop the recording as well, and then we are going to restart from the same link.
Okay.